You know, I was standing out my backyard last night, just doing the typical Tuesday stuff, taking out the recycling, and I just stopped to look up at the moon.
Oh, yeah. It was really bright last night.
Incredibly bright. It was a perfectly clear night, full moon, and I had this thought. If you think about it, it's really the most familiar thing in our lives, isn't it?
It is. It's the ultimate constant.
Right. It's the background wallpaper of being human. We write all this bad poetry about it. We track our months by it. It's this steady, romantic, completely silent presence. It honestly feels like a friend.
Yeah, the watchful eye. I think almost every ancient culture has some variation of that exact idea.
Exactly.
Yeah.
But then I started going through the massive stack of research you sent over for today's deep dive. And I have to say, this stack was significantly heavier than usual.
I might have gotten a little carried away with the source material this time.
No, it's great.
Yeah.
But I realized pretty quickly that my mental image of the moon, this quiet, static, silver rock in the sky, it's completely fictional. It is a lie we tell ourselves to feel safe.
It's a very comforting lie, but yeah, it's definitely a lie. When you actually strip away the mythology and the romance and you look at the sources, you start looking at the moon as a planetary mass object, which is what it technically is.
Right.
The reality of it is just so much more chaotic, it's violent, it's strange, and honestly, it's a little bit terrifying.
Terrifying is absolutely the right word. Because we are talking about a world born from a literal apocalypse, a world that is currently shrinking and cracking like a drying raisin.
Yep.
And this is the part that completely blew my mind in the notes. A world that apparently smells like gunpowder.
It does indeed smell like gunpowder.
Yeah.
And perhaps most unsettling of all, if you look at the orbital data, it's actually trying to leave us.
We are definitely going to get into that breakup story a bit later. But our mission for this deep dive is to construct a real biography of Earth's only natural satellite.
Right.
We're pulling from geological surveys, Apollo mission transcripts, some incredibly dense isotopic data, all to understand what this object actually is. And I think to really understand the moon, we have to start at the very beginning.
The origin story, which in the case of the moon is really a story about the single worst day in Earth's entire history.
The violent birth. Because the moon didn't just float by one day and get caught in Earth's gravity, right?
Mm-hmm.
I remember learning that in school, the old capture theory.
Right. The capture theory was super popular for a long time. It's this idea that the moon formed somewhere else entirely in the solar system, wandered past Earth, and just got snagged by our gravity, like a fly in a spider web.
Just passing by and got stuck.
Exactly. But the physics of that are just incredibly difficult to actually make work. You'd need to shed a massive amount of energy almost instantly to be captured smoothly like that.
Because it's moving so fast.
Yeah, it's mathematically highly improbable. If a body of that size came cruising by, it would likely either just swing past us and get slingshotted away, or it would crash straight into us. It wouldn't just magically settle into a nice, neat, circular orbit.
Okay, so if it wasn't a drive-by, what was it? Because the prevailing theory in the sources sounds like a pitch for a disaster movie.
It really does. The prevailing theory, and this is the one that fits almost all the physical evidence we've collected, is called the giant impact hypothesis. And when scientists say giant, I don't think people realize the scale we are actually talking about here. We mean cataclysmic.
So set the scene for us. We're going back, what, about 4.5 billion years?
Roughly 4.51 billion years, yeah. So picture the early solar system. It is basically a demolition derby.
Just rocks everywhere.
Exactly. It's not the orderly clockwork system we have now where everything politely stays in its lane. There's debris everywhere. Protoplanets are just smashing into each other constantly. Earth is there, but it's the proto-Earth. It's incredibly hot, very volatile, and it's not alone in its orbit.
There's an intruder.
A second planetary body, roughly the size of Mars. Scientists have named it Theia, after the Greek titan who gave birth to the moon goddess Selene.
So we have Earth, and we have this Mars-sized planet, Theia. And they aren't just passing in the night.
Oh, no. Theia slams directly into the proto-Earth. And I really want to be clear about the sheer energy here. This wasn't a fender bender. This wasn't even an asteroid impact like the one that wiped out the dinosaurs.
Which was huge in itself.
Right. But this was a collision between two actual planets. The energy released was enough to completely liquefy the Earth's crust, and it absolutely obliterated Theia.
I'm trying to even visualize this. We're talking about a collision so violent that it turned solid rock into vapor.
Correct. It vaporized billions of tons of rock. It created this massive cloud of superheated dust and molten material. Some of that fell back to Earth, of course, but a huge amount of it was blasted out into orbit. It actually formed a ring around the Earth.
Wait, like Saturn?
very much like the rings of Saturn, but instead of ice, it was made of molten lava and vaporized silicate.
That is just an incredibly metal image. Earth with a glowing ring of lava.
It really is. And the heat was unimaginable. We are talking thousands of degrees. The atmosphere would have been stripped away entirely. Any surface oceans would have boiled off instantly if they even existed yet. It was a total reset button for the planet.
Oh.
But this is where the physics gets really interesting. This ring, this debris field, it formed just beyond what we call the Roche limit.
Okay, yes, let's unpack that term, because I saw Roche limit all over the source material. What does that actually mean in plain English?
So think of the Roche limit as a danger zone surrounding any planet. It's the minimum distance to which a satellite can approach its primary body without being torn apart by tidal forces.
Tidal forces mean gravity.
Yes, because gravity isn't totally uniform. If a moon gets too close to a planet, the gravity pulling on the front of the moon, the side facing the planet, is much, much stronger than the gravity pulling on the back of the moon.
So it's getting pulled unevenly.
Exactly. That difference in pull stretches the moon out. Inside the Roche limit, that stretching force is actually stronger than the moon's own internal gravity holding it together. So the moon just rips apart and becomes a ring of dust and rocks.
So if our moon had formed inside that limit, it would have just stayed a ring forever.
Precisely. We'd have a permanent ring system today. But this debris from Theia was pushed just outside that limit. Because it was outside the danger zone, gravity could safely do its work.
So it started clumping together.
Right. The clumps of magma and dust started sticking together, accreting, getting bigger and bigger, and surprisingly fast, too. Some of the newer simulations in the sources suggest the moon could have coalesced from that disk in less than 100 years.
Less than 100 years. That's a blink of an eye in geological time. Less than 100 years to build an entire moon.
It was a wildly violent, rapid accretion. And because of all the intense heat involved in that process, the infant moon wasn't a solid rock at all. It was a glowing ball of molten magma. The estimates say it had a literal magma ocean that was anywhere from 500 kilometers to over 1,700 kilometers deep.
A magma ocean 1,000 kilometers deep. Just imagining the view from Earth at that time, if you could stand there, looking up and seeing a giant glowing red orb instead of a white one. It must have taken up a huge portion of the sky too, right?
Oh, yeah. Been much closer to Earth than it is today. It would have dominated the sky. But this actually brings us to the biggest scientific puzzle in the notes you read. The chemical mystery.
Right, the isotopes.
Yeah.
This is where the real detective work comes in.
Yes. This is how planetary scientists do forensics. Every single object in the solar system has a totally unique chemical fingerprint based on where it originally formed. We look at isotopes, which are just variations of elements like oxygen.
So Mars has a specific fingerprint.
Exactly. Mars has its own specific oxygen isotope signature. Asteroids like Vesta have another. So logically, you would expect Theia, having formed somewhere else in the solar nebula, to have had its own distinct chemical fingerprint.
Okay, I follow you. So if the moon is made mostly of the wreckage of Theia, which the old computer simulations said it should be, the moon should look chemically different from Earth.
Exactly. It should look chemically like Theia, but it doesn't.
It looks like us.
It looks almost exactly like us. When scientists analyze the rocks brought back by the Apollo missions, the isotopic composition of the moon is nearly identical to Earth. It's like they are identical twins. And for decades, this completely broke the giant impact hypothesis. Scientists were just scratching their heads going, if a Mars-sized thing hit us, where is it? Why isn't the moon made out of it?
That is a massive plot hole for that theory. So how did the sources explain that now? Did Theia just not exist?
No, the physical models for the collision are too strong. We know something hit us. The leading explanation now is that the collision was even more violent than we previously thought. It was so insanely energetic that it caused a massive turbulent mixing of all that vaporized material.
Like a planetary blender.
A blender is the perfect analogy. It essentially homogenized Theia and the proto-Earth into a single mixed system. There's actually a specific term for this theoretical structure in the literature, a synestia.
Synestia. What does that look like?
Imagine a massive donut-shaped cloud of vaporized rock that is spinning so fast it flattens out. Earth and the moon both condensed out of this exact same cloud. They swapped so much material back and forth in that superheated vapor phase that their chemical fingerprints became identical.
Wow. That's oddly profound if you think about it. We aren't just partners in space, we're literally the same material. The moon isn't a stranger, it's a piece of us that got knocked off and reformed.
Or we are a piece of it. It's a shared heritage forged in absolute fire. We are two children of the exact same catastrophe.
That really changes how you look at it up there. It's a sibling. Okay, so moving the timeline forward, we have this cooling ball of magma. It eventually solidifies, the crust forms, and we get the moon we recognize today. But it doesn't just sit there. It starts this intricate dance with Earth.
Right.
And I want to talk about how we actually see the moon from down here. Because there is a phrase that appears in pop culture constantly, and the notes say it drives astronomers absolutely crazy, the dark side of the moon.
Look, it is a fantastic Pink Floyd album, truly one of the best. But it is a terrible astronomical term. There is absolutely no dark side in the sense of a place that is permanently in shadow.
But we only ever see one face, right? The man on the moon. I've never seen the back of his head.
That is true. We only ever see the near side. But the far side gets plenty of sunlight. Think about it. When we have a new moon here on Earth, when the moon looks completely dark to us, that means the far side is completely bathed in full sunlight.
Right, because the sun is hitting the back of it. So why do we only ever see the one face? Is it just blind luck? Did it just happen to stop spinning at the exact right moment?
No, it's not luck at all. It's physics again. It's a phenomenon called tidal locking.
How does that work?
So, think back to that infant molten moon. Earth's gravity is pulling on it constantly. Just as the moon pulls on our oceans today to make tides, Earth pulled on the moon's actual rock. It created a physical bulge in the moon's shape.
Like it stretched it out into an egg shape.
Slightly, yes. And Earth's massive gravity basically grabbed onto that bulge and acted like a brake.
A brake on its spinning.
Exactly. It created gravitational drag. Over millions of years, that drag steadily slowed down the moon's rotation. Eventually, it slowed down so much that its rotation period, the time it takes to spin exactly once on its axis, perfectly matched its orbital period around Earth.
So it spins at the exact same speed it orbits us.
Precisely. It takes about 27.3 days to orbit Earth, and it takes exactly 27.3 days to spin once on its own axis. The end result is that it always keeps the exact same face pointed at us. It's like, imagine walking around a campfire while making sure you keep your face pointed toward the fire the whole time.
You have to spin your body to do that.
Right. You have to turn to walk in a circle, but the fire only ever sees your face.
That is a brilliant analogy. And the far side looks totally different from our side, doesn't it? The sources mentioned that when the Soviets finally sent a probe around back there, the pictures were kind of shocking to scientists.
Oh, drastically different. The near side, the one we are used to seeing, is covered in those large dark patches we call maria, or seas.
Which aren't actually water.
No, they are ancient volcanic plains, huge flat basaltic lava flows. But the far side, it's almost completely devoid of those dark seas. It's heavily cratered, very rugged, what we call the highlands. It honestly looks like a completely different planet. It's much, much messier.
Why the big difference? Why did all the smooth volcanoes happen on our side?
Well, the current thinking is that the crust on the far side is significantly thicker. So back in the early solar system, when giant asteroids were hitting the far side, they couldn't punch deep enough through that thick crust to reach the molten mantle below and let the lava flow out.
Ah, okay.
But on the near side, where the crust was thinner, those massive impacts cracked it wide open like an eggshell, and it just filled those huge craters with dark lava.
That's fascinating. It really highlights how dynamic the whole system was.
Yeah.
Now, earlier you mentioned that the moon is, and this was a great phrase trying to leave us, the Great Drift.
Yes, this is one of those scientific facts that sounds like absolute science fiction, but
Well,
we literally measure it every single day.
How do we even measure that? I assume we aren't using a really long tape measure.
We actually use the Apollo legacy for this. The astronauts left these things called retroreflectors on the surface. They are basically incredibly high-tech mirrors.
All right.
Observatories here on Earth shoot high-powered lasers directly at those mirrors, and we meticulously time exactly how long it takes the light pulses to bounce back. That allows us to measure the distance to the moon down to a fraction of a centimeter.
That is some seriously precise shooting. And the verdict of all these lasers is?
The moon is moving away from Earth at a rate of about 38 millimeters per year.
38 millimeters. I think the notes said that's roughly the speed at which human fingernails grow.
That is the standard, slightly gross comparison we use, yeah. It sounds really small, doesn't it? But over deep geological time, it really adds up. When the moon first formed, we talked about how big it was in the sky. It might have been only 20 or 30,000 kilometers away.
And now?
Now it's nearly 400,000 kilometers away.
Wow. So what is pushing it away? Is it just losing momentum?
Actually, it's gravity again. Specifically, the ocean tides. So the moon pulls on Earth's oceans, right? It creates that tidal bulge, that high tide that travels around the planet every day. But here's the physics trick. Earth rotates much faster than the moon orbits us. A day here is 24 hours. The moon's orbit takes 27 days.
So Earth is spinning really fast underneath the moon.
Right. And because Earth is spinning so fast, the friction of the ocean floor actually drags that massive bulge of water slightly ahead of the moon's position in the sky. The high tide doesn't sit perfectly directly underneath the moon.
Okay, so the water is offset forward.
Yes, and that massive moving mountain of water has its own gravity. It physically pulls on the moon. Because that water bulge is ahead of the moon in its orbit, it constantly drags the moon forward. It gives it a tiny, constant gravitational kick.
Like pulling a dog on a leash.
Exactly. And the laws of orbital mechanics dictate that when you add forward energy to an orbiting object, it moves outward into a higher, larger orbit.
So our own oceans are basically shoving the moon away, inch by inch, like a slingshot that just never stops firing.
That's exactly it. And there is a real cost to that cosmic transaction. Physics says energy always has to be conserved. If the moon is gaining orbital energy and moving away, Earth must be losing energy from somewhere.
Losing it from where? Are we getting colder?
From our rotation. As we push the moon away, the friction of those tides sloshing around is acting as a brake on the Earth itself. Earth is slowly spinning down. Our days are actually getting longer by about 17 microseconds every single year.
Wait. So in the distant future, a day won't be 24 hours long.
Correct. And if you go backward to the time of the dinosaurs, a day was only roughly 23 hours long. Go all the way back to the early Earth, right after the moon formed, a day might have been only 6 hours long.
6 hours.
Yep. And in the distant future, days will be 25, 26, eventually 30 hours long.
That is such a wild thought. We think of a day as this fixed, immutable unit of time, but it's totally elastic. We're literally running out of time or gaining time, depending on how you want to look at it.
Everything in the solar system is constantly in motion. Nothing stays still.
But speaking of the tides, the sources mention it's not a one-way street, right? Because Earth is much, much bigger than the moon. I think the note said Earth is about 81 times more massive. So if the moon can pull our oceans, Earth must be doing something huge to the moon.
Oh, absolutely. We create massive tides on the moon, too. But since the moon has no oceans to slosh around, Earth's gravity creates what we call a solid body tide. We actually stretch the physical rock of the moon.
We stretch the rock.
We do. The moon's physical shape bulges by about 10 centimeters closer to Earth on the near side. It's like slowly squeezing a tennis ball.
The solid bedrock is moving 10 centimeters. That seems like an enormous amount of flex for stone.
It is a lot of stress. And here is the kicker. The moon's orbit isn't a perfect circle, it's elliptical. Sometimes it's closer to us at perigee, sometimes it's further away at apogee. That means the strength of Earth's gravitational squeeze is constantly changing. The moon is being constantly flexed, squeezed and released every single month.
And rock generally doesn't like to be flexed.
No, it's highly brittle. This internal friction and stress causes the lunar crust to crack and snap violently, which leads us to one of the most surprising discoveries of the entire Apollo era, moonquakes.
Moonquakes. I honestly just love that word. But they aren't like earthquakes, are they?
Not at all. On Earth, earthquakes are usually caused by massive tectonic plates grinding past each other. The moon doesn't have tectonic plates like we do. Its crust is one continuous shell. These moonquakes are caused by that tidal squeezing we just talked about, and also the slow cooling of the moon's interior. But the actual experience of feeling a moonquake would be wildly different from an earthquake.
How so? What would it feel like?
Well, if you have an earthquake in, say, California, the ground shakes violently, sure, but usually the seismic waves die down within a minute or two. Why? Because Earth is wet. The crust is totally saturated with oceans and groundwater, and the deep interior is hot and gooey magma. All that moisture and molten rock absorbs the seismic energy. It quickly dampens the vibration.
Like hitting a snare drum that's filled with water.
Exactly, just makes a dull thud. But the moon is incredibly dry, bone dry, and it's cold and rigid throughout most of its crust.
So what happens when that brittle rock quakes?
It rings like a bell.
Literally rings.
Literally. The Apollo astronauts left a network of seismometers up there. When they jettisoned their used lunar modules to crash back onto the surface,